Okay, so welcome everyone to today's One World IAMP Mathematical Physics Seminar. This is a regular seminar of IAMP, the International Association of Mathematical Physics. And if you're watching this on YouTube and if you're new to the seminar series, please go to the M and Phi logo down there. And if you click there, you will see more about this seminar series. Okay, and we also encourage you to join our mailing list. Okay, so today it's our great pleasure to have Horng-Tzer Yau, and he's going to tell us about spectral gap for mixed p-spin models at high temperature. Okay, so the floor is yours.
Right. Thanks a lot for the introduction. And so I will talk about the spectral gap for mixed p-spin models at high temperature. And this is joint work with at the Hikari and Brenecki and Schurz and Changji Xu. So I gave this talk about a few months ago. And so the first half is about something I already said about a few months ago, and the second half is about some newer result. And so for those of you who already listened to the first half, and so I'm sorry there's some repetitions. All right, so now so let me start to write down the models. And I think everybody, I suppose quite a few of you knows already the models, but let me just repeat it. So we are talking about the spin glass models, and with a spin sigma I, sigma j, and with a Gaussian Gij, and which is normal distribution with variance 1. And now there's a temperature here, and you divide by square root n just to make sure that the size is correct. And then there's external magnetic field H. And now you define the Gibbs measures with this Hamiltonian in the standard way. And the Z is a partition function. As usual, I will use this bracket to mean the integration with respect to expectation with respect to this measure. And later I will also use E. So every time I write E is with respect to the randomness, and this bracket is with respect to the Gibbs measure. Now, so if you look at this, and then you find that actually this metric is really a Gaussian orthogonal ensembles for those of you who like random matrices. Now, in general, one can define more complicated models. It's just you can sum over all the spin p bigger than 2, and then you normalize correctly. So this is a correct normalization, taking into account of central limit theorem corrections and scaling. And then this is called a mixed p-spin model, and then there's a beta p, which is now. So the question, so it's known that there's a high temperature replica symmetric regimes, and which is supposed to be simple, but we will see that actually the simple is not actually less simple. And there's also a low temperature region, and which is a replica symmetry break-in case. And so the picture I'm drawing here is for the SK models. And I mean, but mixed p-spin is expected to be similar, but except that this line is we don't know where this line goes. Okay. Now this line is called the AT line. So this AT line, there's a condition, and the condition like that. This Q will satisfy another equation which I didn't write down, but later I will show you what's the equation for Q, and this condition define the AT line. AQ is supposed to be the magnetization, the size of magnetizations. So this is a stationary picture. There's a high temperature and there's low temperature. I'm using the so I'm using this is a beta, and so it's beta small and this is beta large. Okay. Now then there's a fast mixing and the slow mixing. So the picture now is start to become more complicated. It's for the SK models, one expect that these whole regions, these whole regions is fast mixing, and then it's the fast mixing, and you can say the dynamical transition and the station transition actually happen at the same place. But in general, for the mixed P-spin models, there's another line here. There's another line here, which is one people believe that there's another line here, and then it's fast mixing here, and the slow mixing will be here. So it's kind of I think it's very interesting behavior. And on the other hand, if you look at the discrete spin, there's not that much result. So for the discrete spin case, then the fast mixing is proof in this part, and also in this part. So this is what I'm trying to tell you today. And now the slow mixing in the P-spin models is not the, if you don't look at if you don't look at discrete spin, if it's a continuous case, then actually in the so-called spherical models, one actually can see that there is a slow mixing in these regions. I mean, it's not clear that this will really reach this conjectural line, but in any case, so the slow mixing actually cut into the high temperature regions. So the dynamical transition and this state and transition is different. So now for discrete, now the next one. So let me mention how to improve the fast mixing. So there are various ways to prove the fast mixing. So mathematically, usually there's two inequality. One is called the log-Sobolev inequality, and the other one is the spectral gap inequality. So log-Sobolev inequality now typically we stay in the Euclidean space, and if you take a measure e to the minus h of x, and the log-Sobolev inequality is an inequality of this type, f log f. Integration of f log f is bounded by gradient square root f square, and there's a constant gamma. And if this is true for all probability density f, then this say the log-Sobolev inequality hold. Now, typically we know the log-Sobolev inequality, and then this object, this is called the Dirichlet form, and the Dirichlet form will generate the dynamics, time evolution dynamics, and the key is the log-Sobolev inequality will imply a fast mixing of this type. And so the log-Sobolev inequality actually, once you prove this, then you do have the fast mixing in a very strong sense. And spectral gap it's a bit weaker, because spectral gap tell you that it's you take f covariance. So covariance means f minus its expectation. So once it minus its expectation, so f minus expectation, and this is bounded by the gradient of f squared with some constant kappa, which is positive constant kappa, then you say that there is a spectral gap inequality hold. And once the spectral gap inequality hold with this kappa order 1, then this will imply the L2 ergodicity. So all this is well known, and this is spectral gap is weaker than log-Sobolev. All right, okay. So but anyway, now for the discrete case, you can define the Dirichlet form instead of using it. Just change the definition of gradient. The gradient means you flip the spin sigma I from plus to minus. So here is you look at sigma I. So if you change sigma I to minus sigma, is flip one spin and take gradient square. And sometimes actually it's quite often that there's a factor here, Ci. So which I will show you later on. The Glauber dynamics actually is actually really defined with some prefactor here. Now, so there was so for the log-Sobolev inequality for the SK models. Actually, there is a proof by Bauer-Schmidt and Bodinel in 2018, and this is for beta less than 1/4. But this is for SK models, and it's only for the SK model. And then they told there are some various extensions by different group, but on the other hand, this 1/4 was not improved. Now, part of the reason is the interest. I think there's just, in my view, there's a renewed interest of understanding the Glauber dynamics and also this mixing by the Variance, because now the gradient dynamics is extremely popular everywhere in computer science, and also so they also want to study the how do we sample this. How do we sample the Gibbs measures? And in particular, this Araui, Montanari, and Selke, they proved that, or Centeno in 2022, and last year, they proved that for zero magnetizations, and they can have a new algorithm, which is not really the Glauber dynamics. I mean, it's a bit complicated to explain what it is, but I mean, for them, there's no, you don't have to exactly using the Glauber dynamics. So there's so that's why I say it's not MCMC based. It's but they can sample the system with zero magnetization for beta less than 1. You know, it's quite interesting if you think about it. This the first result of in math physics for spin glass, it's actually for beta less than 1 for h equals 0 by Eisenman, Leibowitz, and Well, and it's more than 30 years, and now you see that this condition will appear again, and in sort of statistics and computer science papers, and so it's kind of remarkable. Now, let me see how much time. Okay, so let me just say 1 minute how Roland Bauer-Schmidt he proved, and Bodinel proved this this SK model has a mixing. It's actually a beautiful, simple idea, and it's very easy to see what it is, because
now is this for any magnetic field or?
Yes. Oh. This is for any edge.
Okay.
You see that I draw the picture here, here, and also let me see if I say it here. Oh, I forgot to say arbitrary edge. Okay, sorry. Yeah, what you do is you look at this quadratic piece, and then the quadratic piece, because it's a random matrix beta G, then you just add a constant to make it positive. It doesn't matter. So the constant is slightly bigger than 2, and then this is positive. And then you use the duality, and the sigma q, sigma is written as a sigma dot phi, and the Gaussian integration with 1/q as a covariance. And now the idea is very simple, because now, so the only thing you do is you only have to check 2 things. One is if you condition on phi, then the sigma is a product measure, so there's a spectral gap for the sigma. And the other one is if you integrate sigma, and then you check that you want after integrate sigma is a continuous model, because phi is just a real number. And for the real number, the only thing you have to check is log convexity. So if you check log convexity and it holds, it's beta less than 1/4, and that's it. Because for the conditional phi, the sigma has a spectral have a log-solver inequality because this is just product measures, and then the marginal is also corrected. Marginal distribution of phi is also log convex, and then everything just finished. So it's a beautiful idea. Now, but this idea, if you try this idea in the p-spin model for p bigger than 1, then p bigger than 2, then it's not working. And of course you can still write this mixed p-spin model, some sort of integration like that. But if you look at carefully, you will find that all this this 1 over square root n factor and change to something else, this will make the whole thing doesn't work. I can't say it definitely would not work, but I thought, quite a few people thought about it, and the mixed p-spin case, it's not, at least I don't, it's actually not just a simple, straightforward generalization. This will make it work. Okay, so so for the mixed p-spin models, so this is our result, and so we define the direction form actually in a stronger way. This is the Glauber dynamics. Glauber dynamics always defined with the Koch factor. This Koch factor is this Bi is external. It's an external magnetic field acting on sigma I. Well, I write down this Bi in the case of SK case, but in general, the Bi is just whatever the field acting on sigma I. For example, if you look at this one, so what happens? This is sigma I, and then there are also sigma j, and maybe there are sigma k, and all this acting on sigma I, and then this external field is called a Bi. So in the SK case, there's only j acting on I, so it's a Gij sigma j and plus Hi. So this is the factor you use in the Glauber dynamics. And actually this one is, because it's Koch, so this is actually smaller than the standard direction form. So if you prove something about with this factor, it's actually a stronger inequality. Now the result is with high probability. If this temperature factor is small enough, is sufficiently small, then for any edge, this also for any edge, by the way, this one is also for any edge. Maybe I just add it here. So this is for any edge, for all edge. And then you find the spectral gap inequality holds. So this is a generalization of a small piece generalizations to a mixed p-spin case, and the method is completely different. And so I want to explain some of the proof, and also I want to explain that what we can do to go to sort of maybe to see something closer to understand these regions in a more precise way. All right. Okay. So so now let me just give you a quick overview of the proof of this log-solver inequality, and this is strong mixing. How do you prove it? Now, the strong mixing, there's a method based on convexity method. This convexity method is Bakri-Emery and Breskam-Lieb and heat kernel estimate. I mean, all these methods are essentially convexity based. It's just based on something has to be convex, and in order to make it work. And now they are for Ising type models. Actually, there are a lot of results based on spatial mixing. try to this kind of some sort of devolution, this uniqueness condition, or this some stronger version of the mixing condition. You need some mixing condition, and then later on also, besides mixing, one can use in some sort of coupling ideas and a correlation inequality, which was based on monotonicity of the system. So it's particularly well suited for the IC model. And now this anything based on spatial mixing, you typically need some sort of condition like that. It's if you take correlation function sigma I, sigma j, remember that the sigma I, sigma j covariance, this means this is the standard correlation with mean subtracted. So you typically need this condition. It has to be correlation, has to be summable, otherwise, and it's in absolute value summable. Now for spin glass, I don't know any coupling ideas ever work in spin glass. It just it's not exactly the right concept. And also for spin glass, the reason for spin glass it's difficult to prove. It's actually the correlation function. The size is n to the minus 1/2. So this makes all this method based on spatial mixing. It doesn't work. You know, I look at the problem of this spectral gap of Glauber dynamics. I think in the 1990s, and you know when Martinelli and so on. I mean, so we there are a lot of activity at the time to prove this spectral gap for the Ising type models, and I never understood why the method did not work in the spin glass case, and I tried a little bit and it just didn't work. And now I realize actually it's because for the spin glass, there's something the spin glass is actually very different from the standard Ising type model, because Ising type model high temperature typically has exponential decay, but actually here decay is n to the minus 1/2. Now n to the minus 1/2 is very serious, because you sum over j n to the minus 1/2, this will become square root n. And once you get square root n, of course nothing will work. So I only understood this you know much later. And now the standard way to prove this, I will be careful about the time. So let me not to say too much about the proof. So if you look at two random variables, and with x and y, and now actually you can there's a variance identity like this. Now this identity, the similar identity, also hold for the entropy, for log Sobolev inequality, spectral, you know, for the entropy. But anyway, so it's easier to explain this in the spectral gap. So if you want to compute a spectral gap, this variance of function f, you can condition the variance, compute the variance by, you first condition on the y, you condition on one of them, and then you compute its variance with y given, and then you take expectation. And the other one is you look at the marginal, you integrate over x and you look at the marginal of y, and then you compute its variance in y with respect to the marginal of y. And this is identity. So this identity will tell you, so now this, if you have this identity, and now you assume that condition y, the x has a spectral gap. So this one is directly less than the derivative of f with respect to x. And now the only thing is, and now this one, you also assume that with respect to the marginal of y, you have a spectral gap. So you take a derivative in y of this f with respect to y. Now the trouble of derivative of f with respect to y is the derivative of f with y with respect to y. This is the marginal of f integral x. So you look at this fxy e to the h xy with x integration here, but you differentiate with respect to y. So when you differentiate with respect to y, there will be a 10 differential here. So this gives you this. And there's another term, you differentiate the y here. And also, we will also differentiate the y. So when you differentiate the y in two places, it becomes covariance. And you differentiate y with respect to f becomes this term. So this term is rather easy because you do the Schwartz. When you square this guy, you just take this square. And take this square, you get a term of this square. And you also get this one square, and also there's a cross term. But in any case, you will have to deal with this one. And this term will be vanished if you measure independent, then this one is 0, then you're done. So for independent one, it's trivial. But if your measure is not independent, then what you can do is this one you write as by Schwartz become like this. And now for two variables, it's not a big deal because you only have one such term. But if you imagine you have a large system with many variables, then there are so many these covariance terms, and then you can't really do anything about it. So that's why this is not by itself. That's just like this. It's not particularly useful. On the other hand, there's a way. So I would say about the proof for another 5 minutes, and then I would go to. I will mention some other results later on. So, but let me finish this. So the idea is now it's true. Now we want to apply the previous idea, this idea of the variance in this way, in the following way. So now I look at the conditional measure sigma given by sigma I is this one. So this is one with the sigma I is given here. So now the previous identity becomes the covariance of f becomes given the sigma I compute the variance and then take expectation. The other one is I take a marginal, and then I take a marginal with respect to the marginal distribution of sigma I. So now with the sigma I given, so this with sigma I given here, because the sigma I is given, so now my spin will become n-1 spin. So with sigma I given, I become n-1 spin. So now let me assume that the constant, the spectral gap constant depending on n. Then this will be an-1 times the Dirichlet form of this one. And now I average over all possible I. And then there's inequality. There's a trivial inequality. If I take expectation of this one, and then this would be less than. This will be less than the Dirichlet form of f, which times 1 minus 1 over n. And if I take expectation of this guy, and the reason I get 1 minus 1 over n because the Dirichlet here, you don't differentiate the ith variables. So if you don't differentiate ith variable, and if you take an average, then you get 1 minus 1 over n. So this term, after average, you get this. A minus 1 and df and 1 minus 1 over n. It's very important you gain something tiny, just gain 1 over n. And now the last term, you have fi, but you write this one because you write this one, so you just average over this one, so you write in this way, okay? And now it's average, so there's 1 over n here. So you get this inequality. Now this inequality, and now you have to handle this term, because if there's no such a term, it becomes an is less than 1 minus an minus 1, an minus 1. Then you have finished. So now this is the inequality we have on the previous page. And now if we can prove that this marginal distribution of f satisfy inequality that is less than constant times the Dirichlet form. So this is average of the Dirichlet form of the sigma, the marginal with respect to sigma I, is less than the Dirichlet form of f. And then I allow some epsilon of the original variance and also epsilon of the Dirichlet form comes in. Then I will get inequality. I plug into the previous one. And now this epsilon of ff, I will move to the I will move to the left side, so it becomes 1 minus epsilon over n. And there is 1 over n because there's 1 over n here. So I get a variance less than 1 minus 1 over n, an minus 1, and times n minus 1 of this constant plus epsilon an. And now, because this inequality holds for arbitrary f, so this implies an is less than, and now I divide this over to the other side. And so it's 1, if you look at what happens, it's 1 minus, and then there's epsilon here and there's epsilon here. So it's actually 1 minus 2 epsilon, but because we divide it over, so it's probably something 1 minus some constant times epsilon, an minus 1, and this time an minus 1 times constant. So this will tell you, if you iterate this inequality, an will be less than constant if this one is a stay positive. So this was the idea. Some of this idea was used in the log-solver inequality, and I used this a long time ago in 1993 with Lu, and also with Lee in 1998. And later on, Eric Cullen and Michael Loss and Cavallo, they use quite a lot for these CATS models. So this idea actually this was actually the basic idea, and for the spin glass there are some modifications, and it's a bit complicated. So I will not. I don't want to go to too much details, and so if I have a time, I'll come back to say a bit more. But roughly speaking, so since I have another 30 minutes, so maybe let me spend 2 more minutes to finish this. So the idea is this Fi, this is the marginal distribution of f with respect to sigma I. And the idea is the marginal distribution with respect to sigma I. So actually this is the idea, is f of I. So f of I is a function of sigma I. So it has to be a times sigma I. But then b minus mi is minus its mean, and plus b. And the mi is a mean of sigma I. So if you write in this way, then you find that this a would be just f of sigma I. Actually has to divide it by square root 1 minus mi squared. And so if you find f of I is just this constant a, and the a is this one. And if some simple calculation can show you that this whole variance term will just become f sigma I squared divided by 1 minus mi squared. And then you realize that this is just if you let pi is projection into this vector, and this p is just summation of n projection operator. So you write this becomes f and the projection operator of f. And the only thing you need is you have to prove this projection operator can be bounded by constant times the Ricci form, and then you are allowed to have some epsilon an and epsilon variance term to put it in. And this was more or less the inequality we proved, and they put it in and the previous framework, and it works. So this works for high temperature. And now, so I don't want to go to this to too much detail here. And so let me go to our goal of, so now suppose because we can only prove a spectral gap in high temperature. So the question is, can we get closer to beta equal to 1? Remember we have this picture, right? And then they like this, and then we want to show that we want to show that in these regions there's a spectral gap inequalities. And so for the SK model, so now we look at just SK models, and now we define the covariance matrix. Correlation matrix is Mij. Mij is the sigma I sigma j. This is covariance. So this is really the covariance matrix or correlation matrix, depends on how you like it. And now if one prove this operator norm of M is less than constant, then this means the spectral gap for the linear functions is bounded. I mean, you find that from prove a general spectral gap to this just linear function is so lame, and it looks like you simplify the problem to almost triviality. But let's see if this problem can be answered. Now you see the difficulty here is that this CI can be random depending on G, I, J. All the difficulty is because this constant C can depend on G, I, J. And so now imagine that you write this, suppose you try to compute this CI, sigma I, and CJ, sigma, and sigma J. So just excuse me. So suppose you write down this CIJ, CICJ, sorry. You write, because you want to compute operator norm, so you get CICJ and this MIJ, summation IJ. I think the trouble is this one, it depends on the randomness. So everything depends on randomness. That's the difficulties. And all right, now so the results. So there are two results I want to mention. And one is this joint work with Benecki, Schurz and Shu, and it's just for the H equals 0 case. For H equals 0 case, we can, for beta less than 1, we can prove quite precisely, because these correlation matches were close to 1 plus beta squared minus beta G to the inverse. And this operator norm will go to 0. So it's not just, we not only knows what's this one operator norm is bounded, but we actually can find the exact object that this converge to. And this was proven, I forgot, in last summer or sometimes. And but actually, this they independent prove that the expectation operator norm is bounded. Oh, by the way, our result is with high probability. So I forgot to say with high probability. So their preprint actually appear about 3 weeks before ours, and but we use a different method, and so they use the overlap estimate by Talaguan and the Badina and all this group, and so they prove that this one is bounding. I mean, it's actually quite. Of course, I mean, this is just slightly more precise, but the key is still to understand this is bounded. All right, now what's our idea? The idea, what we are doing, it's this is go back to the 1987 paper, Eisman, Dibowitz, Luell. And if you look at the proof carefully, so what they are doing is really the partition function has a way to write it as a cell-avoiding path from I to J in n vertices, and then with a factor beta G of E. This is slightly the correct way to write is slightly different, but anyway, roughly speaking, this is the way to write the partition function. And so what we prove is this expression and this correlation in the Frobenius norm actually go to 0. And then we also prove that this object, and if you expand this matrix, is exactly this object in operator norm equal to 0. So it looks like this is a very happy ending, and it's there's a way to understand this and quite nice for H equals 0. On the other hand, if you look at H non-zero, I mean, you thought this is completely trivial, but actually, if you this idea in the spin glass, once its H is non-zero, so far nobody know how to make it work. I don't, this is for 30 years. The extension of this one to H is non-zero is. Nobody know how to make it work. I mean, it sounds like you find it very strange. How can this H non-zero will change so much? And the reason is because once H is non-zero, then the magnetization Mi, this is non-zero, and also this quantity is I dependent. And this quantity is I dependent, and this quantity is Mi also dependent on the G, the whole matrix G. So if you want to write the e to the Gij, sigma I, sigma j, if you want to expand this guy, and now, I mean, the idea, of course, you want to center this one, and plus Mi, you can write this way, and you want to centralize, but because all the Mi are depend on randomness, and anyway, it just didn't work. So this idea, I don't know, I can't really explain why, but if you write a sigma I in this way, and you start to shift the expansion, eventually, because Mi depending on the randomness, it will not work. Or I shouldn't say it will not work. At least I don't know how to make it work. So now let me explain to you what happened in high temperature. And so in a high temperature spin glass, the quantity Q, the quantity Q is defined as standardized Mi squared, magnetization squared, and average. And this will converge to a Q, and Q will satisfy this equation. So this is, I don't know, it's some sort of type equation type. So this magnetization will satisfy this equation. And then the AT condition, or the AT condition means this Cauchy mass for this one is less than 1. So this AT condition. Now, you find this AT condition, if you've never seen it before, it's hard to imagine that why the equation relation look like that. And the reason. So now let me explain a little bit what happened is now the AT condition actually, now there's another condition slightly stronger than AT condition called I call it AT1 condition. So now to explain the AT1 condition, now so there's in the spin glass there's a quantity called one step replica symmetry breaking free energy. Now this is assumed that the overlap of the Gibbs state structure has a tree structure, but then it's just one level. So if you think about this Ren and Graham picture of the well, it's just one step. So the one step replica symmetry breaking free energy, this can be computed explicitly is given by this formula. So this formula looks like a nightmare, but everyone in the spin glass knows that this is what you would get from the one replica symmetry breaking. So the one replica symmetry breaking, if you compute explicitly, is defined by two quantity Q and the Q prime, and then there's number M, and now so the phi of Q, this actually depends on Q, but usually always think about this as a function of M and Q prime. It's written in this way, and Q is considered fixed. And now this one is a lot more complicated. So you first take a Cauchy and to the m's power, and you integrate out z prime. And after you integrate z prime, you integrate out z. So this one is z. So you integrate z prime, integrate z. You first take a Cauchy, and then you take integrate z prime, integrate z. Anyway, this formula, if you've never seen it before, it's fairly difficult to see what it is. But anyway, this is called one replica symmetry breaking free energy. And if you take this one replica symmetry breaking at the point 1 in Q, if you say Q prime equal to Q, and the M you set equal to 1, then this is exactly the replica symmetric free energy. So the high temperature region is defined to be, in a way you can define the high temperature region defined to be this free energy is is actually equal. It's actually equal to phi 1q. Then this would be, if you compute this guy and you compute this guy, if you find that they are the same, then that's the high temperature region. So, but the condition is, instead of making this comparison, one take the infinitesimal versions, and this is slightly stronger versions. So this is a comparison of phi 1q and the phi mq prime. And this, if the derivative is negative, then this is called AT1 condition. So AT1 condition is some sort of infinitesimal condition of the comparison of a one replica symmetry breaking free energy and the free energy comparison. So one has this condition, and also it's a strictly less than 0. It's not less than or equal to 0. So and now what people can prove is it's under the condition of this AT plus this AT1 condition, then the free energy were given by one replica symmetry, by this replica symmetric free energy. And this is high temperature region. So AT plus AT1 imply high temperature regions. And now this is widely expect this AT will imply this AT1 condition. And the reason, and now, but this looks like a completely obvious, because this is just a two Gaussian integration. This is Z and Z prime, two Gaussian integration. And it's just a calculus problems. The AT will imply AT1. But nobody can prove it. It's I don't know what to say. I mean, this is you may give it to undergraduate students who know just what's the Gaussian integrals and try to see if he can prove it, or he or she can prove it. It's really if you just take this formula, this is really just a calculus. But anyway, just anyway, people believe this is correct. So our result about the operator norm of the covariance matrix is the correlation matrix, the probability of a correlation matrix bounded by k epsilon is bigger than 1 minus epsilon. So we assume that both AT and AT1, just like Tarawan, and then we prove that this operator norm is bounded under this assumption AT plus AT1. And in particular, for beta less than 1, this condition AT and AT1 holds for beta less than 1 for all H is correct. So we didn't really prove the spectral gap up to beta less than 1, but if you like, we can only do this for the linear function. So that's that. And now for a few minutes, I would like to explain what's the proof going to this work with Benecki and Changji Xu. And now, so if you look at the overlap of spin glass, it's written in this way: sigma I1, sigma I2, and right. So this is standard overlap of spin glass measures. And now the Tarawan proved that under the AT and AT1, then this overlap is exponential concentrated. It's actually remarkable strong inequality. So with this inequality, you know that this overlap quantity is exponential localized, exponential concentrated. So there are lots of consequences that can be derived for this one. And actually, we use this to prove the following bounds on the correlation matrix. So define this. This is called a truncated or this corrected correlation function. You take a log of H, but now your H is H1, H2 to Hn. They are all different, and you define the correlation of by taking the log and take a derivative. And so this is the k-point function is defined this way. So now the k-point function, I mean, this is really corrected k-point function. So k-point function, we prove that from this one, there's a whole family of inequality about this correlation function can be proved. So for example, we can prove this is correct. Now this MIJKK. So why do I want to write this spatial example? Because this example shows what it is. And what I'm trying to emphasize the two things. One is this one is very useful. The second thing is actually even with this one inequality, you cannot prove this in the strongest sense. So the 2-point function MIJ. So we know the 2-point function ij. So we believe the MIJ is less than 1 over square root n. But then if your MIJ case, it would be 1 over n. And so, but then on the other hand, you increase another k, it doesn't really change too much. But if you take an average over k, this will also give you something. So that's why we got the result is n3 minus 5 over 2. I mean, it's not optimal, but it's also better than it's highly non-trivial. So now if I want to prove this this operator norm M is bounded, it's so now this overlap can help this moment, but there are lots of restrictions. So that's the first sentence. Now the operator norm, how do we bound the operator norm of a matrix? Actually, we can only do this a stupid way. We only do this Hilbert-Schmidt norm, and this is a terrible estimate because this overestimate by a factor n. And we don't really have a good way to bound operator norm. I mean, of course, sometimes we try to compute and we try to do cancellation, but the error term is always just using the Hilbert-Schmidt. So it's a terrible way to do it. But so that's why it makes the problem much harder. And because of this overestimate factor n, so it's a problem. And now the last thing I want to explain is M is a random matrix. So why this M is random matrix? So let me explain why M is a random matrix. Now, in the spin glass, there is something called a tap-free energy. So tap-free energy is a solid Anderson and Palmer. They claim that the free energy of the spin glass of the SK model, it's actually given by the minimum inf of this term, of the tap-free energy. Now, this tap-free energy is quite strange. It's what you do is with a sigma, G sigma, you change the sigma to M. And now this one is still the same. It's H sigma I, just change to its mean, HMI. And now there's a correction term. This term is sort of, I don't know, and people always call this either call it Onsager term or Ito terms. Anyway, there's some sort of reaction term. There's some nonlinear term like that. And actually, you need to add this term in order to make tap equation correct. So I don't really have a good explanation of why you add this term, but adding this term is important to get the tap equation correct. And now this one is the entropy of a discrete system. You see this 1 plus x log 1 plus x, 1 minus x log 1 minus. So this one is the entropy term. And so the energy minus entropy is free energy. And now, if you look at critical points of this equation, then you get this one. And this is the so-called tap equations. Now this is a critical point, and because of the log, so that's why you get tangent, you get like that. And now, if you look at second derivative of the tap free energy, you look at second derivative, it's there will be a diagonal matrix. This diagonal matrix coming from this term. Well, I'm coming from this term and also from this term. I mean, also mixed together. So there's a diagonal one. The diagonal one is 1 minus mi squared. So there's 1 minus mi squared inverse. And then there's this G is random matrix. And this term, this term will give you this this A will give this MIMJ. It's a projection. This is one-dimensional projection into the M direction. And then there's also beta squared 1 minus Q. And Q is now this one, 1 over n summation mi squared. So the conjecture is one expects the free energy M. this correlation matrix is given by the inverse of the hashing. So inverse of hashing is given by that. And this guy, this. And now this one, it's now you see that now the problem has become very interesting because this is random matrix G. And this random matrix G is correlated with this lambda because lambda has 1 minus mi squared. So they are correlated. And the A also depending on mi, mj, they are correlated. But A is rank 1. So A actually in many cases, if you don't show the M is bounded, A actually is not very important. But this one, lambda and G, they are two correlated random matrices. And you take the inverse of this. And this Q, even though it's this guy, but you can say that you can replace this Q by the solution of this this equation I mentioned previously about the equation of Q. So the M is really, I find this incredibly interesting. Is the spin glass, the correlation matrix become a random matrix. And now, I have a few minutes. So let me just mention what's the idea how we prove this theorem. This M is bounded. So we prove two preposition. I call it preposition A and preposition B. Preposition A is we prove it with high probability. The operator norm of M is bigger than the conjectural one. I mean, with A drop out. This one is bigger than if this it's actually this is less than this inverse operator norm, because if once it's bigger, then the probability is small. So this is one inequality we prove. So this inequality relate the operator norm of M to operator norm of this the inverse of this matrix, which was a conjecture by the tab equation, by tab free energy. And now the other thing is this is purely random matrix question. I mean, I look at this one. I say that to prove this is bounded under the AT condition. I thought it was trivial, but actually it's highly non-trivial. It's also non-trivial, and for people like me working on random matrices for the last 10 years, it's really I don't know what to say. It's such a simple question, but then it becomes so difficult. And the reason is because this function, the dependence of this function on G is high. It's very sophisticated. And so under the AT and AT1 condition, we also prove this is correct. Of course, right now I can't really show that because the time is almost finished. So I can't really tell you how to prove that. But roughly speaking, we prove the tab equation. We prove this tab equation called tab 2 equation. This is the second tab equation. The tab equation. So the tab equation is the magnetization depending on the equation for magnetization is called tab equation. But the tab 2 equation is this equation for the MIJ. The correlation matrix has an equation. So the correlation function has an equation. So we first prove this correlation one equation called tab 2 equation. And now we did not relate it to the MKJ, but we relate to MKJ with a sigma I set to 0. So this is if you work on spin glass, you know that all the matrix sigma, all the spin sigma j were acting on I, but then there's also reaction on I back to sigma j. So this one sort of take out the reaction of I back to j, and so this is called MG. So you take out I here. And then we prove this tab 2 equation is correct under the AT and AT1 condition. And so this is one thing. And the other thing is, this I will not go into detail. The other one is to prove this random matrix condition that the preposition B is AT plus AT1 will imply that this operator norm is bounded. And I just want to say a few keywords. Actually, we use the three results. One is we use the Bolhausen construction in 2018. And this Weigel chance result in 21 and the Centennial in 22. And the Bolhausen's result is Bolhausen has the iterated construction of a tab solutions. And it's remarkable. This tab equation has a solution itself is highly non-trivial, but Bolhausen proved that here's iteration to just solve the equation. The solve equation, there's iteration. So now I don't have time, so I will not go through this. And then the Chen proved that if you assume the AT and AT1, he proved that Bolhausen iteration will give you the correct MI square. So in the Bolhausen iteration, there is a K, it depends on how many steps you iterate. As K go to infinity, then this will actually converge. And the last result is by Celentano, and Celentano has a great observation that this Targman's result, that this Bolhausen result, can be used to connect with if you use this together with the Sudakov for the inequality, and then this can be used to prove that this metric is positive. So if you combine these together, and that's a preposition B. And so so I don't want to so let me just finish this by say a few open problems. Actually, the proof that spectral gap and logs over inequality up to AT line. I think this is I mean, it looked like and how should I say? I mean, one might say that high temperature of the spin glass is not the most interesting regime, but actually you find that even a high temperature, it would be very disappointing if we cannot even show that it's mixing high temperature for the SK model. And now, of course, we also want to see that the correlation matrix and this in operator go to 0. Actually, if you don't assume the operator no, if you use some other weaker, for example, if you just look at matrix IJ and IJ, actually we did prove something like that. But if you want to operator no, we can't prove it. All right. So now and also for the, I think this one is I mean, for me this was the more it's probably more interesting. It's you want to find the exact regions that the p-spin models has a spectral gap is positive, uniformly positive. Actually, there's not. I cannot even find the conjecture of where this line is, and there are some conjecture in the spherical models, but for the spin glass itself, this is actually there's no conjecture. Okay, let me put it this way. I don't know there's a precise line people conjecture is a correct one. Okay, now so there's other question is, are there any other methods? So I don't know either. I also don't know if there any other method. And also so there are many different type of spin glass models, and we just did the standard one. So are there whether we can do it for some other models? All right, so I think I will stop my talk here. And thanks a lot. Thank you.
Yeah, thank you, Yao, for the beautiful lecture. So I think we have some time for questions and comments. So anybody, just please unmute yourself and ask. If not, let me ask some questions. So, so this correlation matrix M is basically an equilibrium quantity, right?
That's right.
Yeah, but is the philosophy that it contains some information, essential information about dynamics? Yeah.
Actually, so there are two things. So let me find this. So of course this is special case of a correlation function of the spectral gap, right? So linear function spectral gap is exactly this operator norm bound. But it's actually also more than that. If you can prove that if you can prove the sup over M for any subsystem I1, I2, IK, and operator norm, if you can put, and this sup over sigma 1, sigma I1 to sigma IK, if one can prove something like this is uniformly bounded, this will also imply I think this will imply both logs of inequality and also spectral gap. There's something like that, but I mean, it's some sort of now. This was not exactly a theorem, but sort of people believe that this is correct, and so to understand this correlation matrix, it's actually quite important. So, of course, I mean, right now, what we are doing is really just look at a very special case of a spectral gap for the linear functions. But if you look at all the proof, for example, like all the proof of the spectral gap, especially I think Rowland's result for the IC model and so on, is also for the IC model spectral gap is also the log Sobolev inequality, also completely based on an estimate like that. And so this usually is viewed as a first step to understand the spectral gap. So, I mean, I can't really, this. Besides that, I find that there is a connection between the spin glass and the random matrices, and so to me, it's interesting.
Yeah. So probably this is a stupid question, but so you mentioned this complicated phase diagram for the P spin glass models.
Yes.
In which case the phase boundary differs in the equilibrium case and the dynamical case.
Oh,
it's very interesting.
I think people believe that as long as as long as P is not equal to 2. This one is
so the question is, is there any chance of observing this phase diagram by looking at like this correlation matrix M and some other more?
Oh, yes. I believe that for example, for P spin models, my personal belief is the fast mixing regions. You can define the fast mixed regions by correlation matrix of Pareto norm is bounded. I think this one and this one bounded. They are the same. So of course you can say, well, I just define this by this condition, but the question is whether one can find a sort of
and
more analytical.
So you still don't know the AT condition for this case.
Yes, in the SK model, these two lines sort of coincide, but this is only in S. I think I believe that this is a general phenomenon. Here, this is general phenomenon, and this one is only for SK.
Very interesting. Any other questions, comments?
So maybe one question. Is it possible to look at other graphs than the complete graph, like a hypercube, or regular graphs with diverging degrees?
Oh, you can prove that one can prove the high temperature. There's a fast decay of spectral gap for even if you're Gij sigma or sigma j. So if you write like write like this, and no, not I less and j. Now this I and j are for example, like ice in spin glass. And you still can prove high temperature. There's a spectral gap, but because but there's no way you can get close to the critical temperature. There's it's just there's essentially nothing is known about this guy in dimension 3 or something, or even high dimension. So given that we don't have much understanding of this in high dimension, even in high dimension, and also about its critical temperature, so it's not even clear to prove very high temperature there's a spectral gap really meaningful, because over there you are not using the Gij is random. You basically just say for arbitrary coupling is still correct. So you don't really, I mean, here it's interesting because you have 1 over square root n summation Gij sigma I sigma j. So this is 1 over n. By the way, this is different from the Q revised. Q revised is 1 over n. So here has some new phenomenon. But once you go to the Ising spin models, the Ising type, then the Gij is still order 1. I mean, of course, depending on temperature, order 1. But then this is less interesting because the result will be uniform with respect to Gij. So I, of course, I mean, for the Ising case, anything you want to close to the transition, then it will be incredibly interesting. But because we don't know any stationary result, and so there's nothing we can do.
So by the Ising case, you mean the short range Ising type?
Yeah, the short range.
Mm-hmm.
So short range, then
we don't know anything. Yeah. Good. Any other questions or comments? Okay, if not, let's thank Yao again. Thank you very much.
Thank you. So bye-bye.